Hey guys, welcome back to another Leetcode video. Today we're going to be looking at Leetcode 323, number of connected components in an undirected graph. And this is a medium level graph problem, and because this is a Leetcode premium question and I don't have Leetcode premium, we're going to be using Leetcode.io to solve this problem. So the same problem, just being solved on a different platform. So we're told that we're given an undirected graph with n nodes, and we're also given an edges array where edges I equals a and b, meaning that there is an edge between node A and node B in the graph. And the nodes are numbered from 0 to n minus 1. Okay, so we need to return the total number of components in that graph. So in this example, we're given an output of 1 from our edges, because if you think about it, 0 is connected to 1 and 0 is also connected to 2, so there's only one component. Let's look at another example where we have two components. Let's say we've got let's say we've got 0, 1 and 2, if I can make this a bit better, and then we have 3 and 4. Okay, so if we were to group these together, let's say we've got, in our array all the edges line up like this, so we'll end up with two components. But how can we know that for sure? So what we can say is, in my previous video I did the solution using depth first search, which is an optimal solution, but the algorithm that is pretty much made for this kind of problem is called union find, and it's where we use something called path compression, where we group nodes to a single parent. So in this case, 0 is a component for component 1, and 3 is the parent for component 3, and we set all nodes in this component group to have a parent node of 0, or of that parent node in that component. So I'm going to actually show how this parent matrix looks like with this parent array. So initially each node has a parent set to itself, so 0, 1, 2, 3 and 4, they all have themselves set as their parent. So let's say we're going through this graph, so we go to 0, and 0 has itself as its parent, so we can return 0. We don't need to do anything, we leave it parents as it is. When we go to 1, we can see that 1 is also its own parent, and we make it equal to 0. So we set 1 equal to 0. So now 1 has one's parent is 0. But let's say 2 isn't connected to 0, 2 is connected to 1. Well then, you'd expect, okay, let's set 2's parent to 1. But with path compression, what we can say is, what is 1's parent? Well, 1's parent is 0. So instead of going to 1 and then 2, why don't we just set 2's parent directly to 0? This is path compression. So now 2 is also equal to 0. And what about 3 and 4? Well, 3 and 4, we know that it's a different component. So 4 is connected to 3, so the parent of 4, we set it to 3. And now if we look at our set, we can see we only have two sets of numbers. We have 0 and 3. So we have one component here and one component here. So again, finding the parent, our root parent for each node, uses the find function, and when we merge, or when we unionize nodes into single components, that's called the union function. So I hope this makes sense, but it will make more sense as we actually get coding. So let's hop straight into the code. Of course, we're going to be using Python for this, and I'm going to set our parent list, like we said, to be each node has itself as its parent. So I for I in range of n. And our find function. So our find function is going to take in a node and return its parent node, or it's like the highest it can go in terms of its parent. So if parent x does not equal to x, so it's not its own parent node, in that case we keep bubbling up until we find a node which only has itself as its parent node. So we're going to say find parent x, and then if not, of course, we're just going to return parent x. So that's our find function written, and then we want to write our union function, which takes in two nodes, and we get the roots of both nodes. So we're going to say root x is going to be equal to find x, root y is going to be equal to find y, and then if root x does not equal to root y, in this case we're going to set the parent of root y equal to root x. So parent of root y equal to root x. So what we're doing is we're getting the parent, and if they're not already equal to the same parent, then we're setting each node equal to a common parent, in which case this is going to be x. And now we want to do this for each edge in our adjacency list that we're given. So we're going to say for x, y in edges, union x and y. Okay, so once we've finished this code, what are we going to have? Well, our parents list is going to look something like this. It's going to look something like 0, 0, 0, and then 3, 3, like we discussed before. So we can see we have two distinct groups just by looking at the distinct numbers in our set which point to parents. So what we can do is we can put this all in a set. So we can set the roots equal to, or just our result, actually result equal to, let's create a set where we find I for I in range of n. So for each number for each node in our graph, we find its parent, and we put this in a set, and then we just return the length of that set. Let's run our code, and we pass the sample test cases. Let's submit our code, make sure we pass all test cases, and we do. We pass all test cases for this problem. So in terms of time complexity, guys, we're looking at an O of n time complexity, and space complexity is also O of n, a worst case scenario. So with that being said, I hope you guys enjoyed this video, and I'll catch you in the next one.